So, good morning. Today, as I wrote you on the Moodle, we will do something a bit different. We'll do the first hour a bit more concise on storage, which is basically the last technology that you're going to see in the course, apart from the guest lecture on fuel cell next week. In the second hour, we will see more in detail. So Luis will give you a quick feedback about, general feedback about Milestone 2. And then I decided to take this hour to give you an introduction about the model that you're using, in the sense that many of you, and we're happy about that, are asking questions about what's behind the scene, so behind the Excel file. So this was intentional from our side. We didn't want to overwhelm you with a lot of text files and so on. Now that you are asking for this information, we will show you as an additional possibility what's behind, so you gather a better understanding of what's going on. So it's not mandatory, of course, to know all these things for the exam. It's mostly that we think it can be interesting for you to just not execute something, but also understand what's behind. I mean, at the end of the day, that's the goal of the course. And so this will be in the second hour. In this hour is about storage. So storage, now you have seen, you started in the course with the fossil resources, and now we are moving towards the renewable part. So storage becomes a key technology in this circumstance. When you have a lot of renewable, especially the so-called stochastic or intermittent renewables, storage is very important. So the idea of this lecture is to give you an overview of how energy, not only electricity, can be stored in energy system, and what are the key characteristics of the main technologies that you can have. So the outcome of this lecture should be that you have an idea of what is the efficiency at which you can store electricity or energy, at which time scale, so if it's around seconds, if it's for balancing the grid and so on, and how do this technology works, at least in terms of general principles. So in general, if we look at the definition that the International Energy Agency gives of energy storage, we see that the storage technology in general are technology that absorb energy, store it for a period of time, and release it to supply at a later stage. So the key thing that the storage technology does is to basically separate supply, decouple supply and demand. And these are different goals. As you can see, here is a graph that I think also Professor Hausner showed last week. When you have, for example, intermittent renewables, like a graph of solar here in a particularly cloudy day with oscillating clouds, you see that your panels can be subject to quite a lot of variation. And so if you want to meet the demand, you have somehow to have some sort of storage there. Not only that, actually, storage can also enable a better energy access, can enable to transport energy in space, something that we don't think about very often. And in general, it allows us to have a better use of resources, in the sense that we do not need necessarily to consume everything at the time we produce it. Storage allows to give us a time shift, let's say. And here I show you some data. So you know that renewables such as wind and solar are intermittent. They are not only intermittent hourly, they're also intermittent over the year. So you know that the solar panel will produce electricity for around 10–20% of the time at equivalent full power in a year, whereas wind energy will have around 20–40%. And you see here some graphs taken from the literature. You see that, for example, in Germany, I think this was from the German grid, you can have variation in wind power supply of the order of magnitude of 400 megawatt in 15 minutes. This means that basically half or a nuclear power plant shuts down immediately, right? So, of course, intermittency of renewable is a problem. Since we're also towards the end of the course, let's try to give a look at something, let's say, in a bit more calm way. Let's give also another perspective. I would like to start this lecture with this video. So this video is from Emory Lovins, which was one of the pioneers of energy efficiency, which questions the topic, or at least the argument against the intermittency of renewables. And I think this is a good way of introducing the storage topic in this case. So it will last 4 or 5 minutes, and then I'll continue with the technologies.
Thank you so much for being here.
Solar power is scaling up faster than cell phones. For 6 years running, half the world's additions of electric generating capacity have been renewable, and the fastest growing parts have been the modular mass-produced renewables like solar and wind power. In each of the past 3 years, they've added over 80 billion watts and $1.25 trillion of private investment. So America now has more solar jobs than we have coal or steel jobs. China last year added more solar power than the United States has. And the year before, China got more electricity from wind power than from nuclear power. Nuclear and coal plants prospects are fading worldwide because wind and solar power are cheaper and can also make grids resilient, preventing cascading blackouts. But these modern renewables also scale up in a fundamentally different way. Traditionally, we built giant cathedral-like power plants, each costing billions of dollars and taking many years to license and build. But now each year you can build a factory that produces each year thereafter enough solar cells to generate each year thereafter as much electricity as your cathedral ultimately will. So solar output scales up incredibly quickly. Mass-producing solar and wind equipment makes it cheaper, so it grows faster. So it gets cheaper, so it grows faster. In 20 states today, entrepreneurs will put solar power on your roof with no money down and meet your utility bill, and soon they'll offer cash back. Yet, many people still claim that solar cells and wind power are too variable to produce much electricity reliably because we can't cheaply store huge amounts for when the sun doesn't shine or the wind doesn't blow. That's a myth. We do not need a storage breakthrough. We do not need supposedly 24/7 baseload coal and nuclear power plants to keep the lights on. And here's why. First, variable does not mean unpredictable. We can predict solar and wind power at least as accurately as demand. In this stormy winter month, forecast output from all the French wind farms almost exactly matched their actual output a day later. But also, we built the electric grid because no kind of power plant is 24/7. They all break. Those giant power plants are shut down about 10 or 12% of the time, losing a billion watts, maybe in milliseconds, often for weeks or months, often without warning. The grid handles this intermittence by backing up failed plants with working plants. In exactly the same way, but often at lower cost, the grid can manage the forecastable variation of solar and wind power by combining them with renewables in other places or of other kinds. So let me show you how this can work. For example, the isolated Texas grid's summer electric loads can get much smaller and less peaky with more efficient use profitably. Now, combining 86% wind and solar power with 14% other dispatchable renewables creates surpluses that can charge up ice storage, air conditioners, and electric cars. And then recovering that distributed storage when needed and filling the last gaps with unobtrusively flexible demand can then deliver 100% renewable electricity every hour of the year with only 5% left over. Using such choreography, some European countries without adding bulk storage are already delivering 25 to 58% renewable electricity, far more reliable than America's. Iowa and South Dakota as well are over 1/4 wind powered today. So they in Europe have already far transcended renewable power's supposed reliability limits. Whatever exists is possible. The National Renewable Energy Plan has also choreographed reliable 80 or 90% renewable electricity for the lower 48 United States. Bottom line, bulk electricity storage and fossil fuel backup are the costliest ways to make the grid more flexible, so we would use them last, not first. A breakthrough in cheap bulk storage would be helpful, but not vital. We needn't wait for it, and the market isn't waiting. Only the myth holds us back. Thank you.
So the key message of this, I will say, of this video is the one that he gives at the last part. So we're not saying, of course, that intermittency in itself is not a problem, but there are good arguments against the fact that we can only use wind when the wind blows and the sun when the sun shines. We have technologies, storage technologies already existing that we'll see today that can help with that. And as you see, most wind farms already have very big lead acid or lithium ion batteries that can already balance quite a lot of variability. And then the variability doesn't necessarily mean uncertainty. So it doesn't mean that we are in a situation in which we don't know anything about what will happen. Actually, day ahead forecasts work pretty well, and normally it's a matter of cost more than a matter of technical feasibility. So when we classify storage technologies, we have different ways of classifying them. A typical classification is between thermal and electrical output, so based on the output. They can be classified based on the time scale at which they respond. So some storage technology that we'll see today work mostly on the seasonal or hourly storage level. So since hourly, we start talking about long-term storage. Some technologies instead work at the second level. So they work in balancing the grid, frequency stabilization in the grid, or what is called arbitrage, which is basically contracting cost on the spot market and so on. Different technologies can serve to different purposes. If we look at long-term storage, basically what we can do is mostly either converting electricity into fuels, or compressed air storage, or pumped hydro. If we look for short-term applications, normally we go towards batteries or towards capacitors and supercapacitors, let's say. A key characteristic of storage technologies is what is called energy density. So how much energy we can store in a given kilogram or meter cube of storage technology. So you see, for example, pumped hydro storage is the technology, as we told in the past, with a very low energy density. We need large amount of water in order to store it. So we are in the order of magnitude of I think, if I'm not wrong, it's 1 kilojoule per kilogram. And we go towards lithium-ion batteries or so on, which starts to be in the order of 500 kilojoule per kilogram, up to fuels, which are several megajoule per kilogram, okay? So the density is a key parameter here. And if we look at statistics concerning solar storage today, actually, if we look around in the data, and that tells a lot about how storage is developed up to now, we don't find really good comprehensive global data as the ones I've shown you around. We normally only find data about big installations. And when we talk about big installations, it means that we have very good data about the pumped hydro power plants. We have few data about the rest of the technologies. So basically, if we look at the data available, we can see that pumped hydro storage is by far the most used technology. The other technologies are so far, let's say, marginal in the market. And another thing is that I will talk about different technologies today, such as batteries, pumped hydro storage, compressed air. Is really mostly an overview of what there is available and the key principles. Just remember that some technologies are already there. So some technologies are developed, they are commercial, they are economical to use today. Some technologies, such as, for example, new types of batteries, such as flow batteries, thermochemical storage, and so on, are at the more research stage of development. I would say that all the technologies that are in this area here, they are available to use or pretty close. The ones that are on the left side of the diagram still will take some years probably to become fully commercial. So I will give you an overview of the available storage technologies, differentiating them by the principle, the physical principle they use for working. So I will divide them into potential energy, mechanical energy actually, so which is divided into potential energy, which is gravity basically, and kinetic energy. Then there is the thermal energy storage, electrochemical, which is basically batteries, and chemical, which is conversion of power to fuels. Pumped hydro storage is the first one. As you might remember from the lecture of hydro, we had this graph showing you how we can, from an amount of water in a reservoir, produce power. In most cases, what we can do is that a turbine is often reversible, and we can use the turbine as a pump. So what we do is that instead of turbining the water available in the upper reservoir to the lower reservoir, we pump up with power available water from the lower reservoir to the upper reservoir. Okay? So this is the very simple principle of pumped hydro storage. And the difference is that it's the same equation, it's just that in this case you have to add the losses. When you turbine, you have to remove the losses from the equation, but exactly the same application of the Bernoulli principle for the storage unit. So if the storage technology works like, a pumped hydro storage technology works like that. When we have excess electricity, when we want to store electricity, we pump it up. So we use the turbine in pump mode. When we want to use electricity, we turbine it. As I said, we already discussed these things in the previous lecture, but it's a technology based on the potential energy of water. So the mass times the gravity times the difference in height. It's a low energy density technology because we need a large amount of water. So we are in the order of magnitude of some thousands, let's say at least 1,000 meters cubed to store 1 megawatt hour of electricity. It is a very mature technology. We know quite well how to use it, and we can also use it for long-term storage. So we can also use this technology for hours and for months. And if we look at the key characteristics, we have basically two types of pumped hydro storage plants. One is the pure pumped hydro storage plants, which means we build the dam just to store energy. We don't have any river coming in the upper reservoir. We just fill it up and with the lower lake. And we have often what are called mixed pumped hydro storage, which means we have a dam with already river inflows on the top, and we also use it for storing energy with a lower basin. So we have a mix between the renewable part, which comes from the river inflows, and the storage part, which comes just from the lower basin. If we look in Switzerland, Switzerland is a pretty interesting country because it has a large hydro capacity, one of the largest if we look at gigawatt installed per capita. We use dams in two ways. So the dams, more or less, and hydro run-of-river plants have already reached their maximum potential, more or less, in Switzerland. The new technology we're building is basically only for pumped hydro storage. So if you look at the power consumed for pumping, up there, from 2016 to 2017, it has increased quite a lot by more than 1 terawatt hour. So there has been new installations of pumped hydro storage and more use. And if we look at how we use the dams in Switzerland, actually, we do both things. So there is pumped hydro storage can be used for day-night dynamics, which means often this was done, especially in the past, now a bit less with France. Cheap nuclear electricity coming from France is stored at night, and so the high price just for financial reasons during the day. This is coming a bit less. What we do a lot in Switzerland is we use a lot of seasonal storage. So the goal, the dams operator, what they want to have is to try to have the dams full at the end of summer, so they can balance the deficit of electricity they normally have in winter months. So you'll see that the dams try to reach their maximum capacity at the end of the summer, and then they will use it in winter. If you look at the graphs, and we'll discuss this later, how storage works in the energy scope model that you use for our project, that's exactly what the kind of behavior that storage, the pumped hydro, let's say, has in Switzerland. And this is, for example, one of the new installations that you have. You remember that we talked about Francis turbines last time that we use for medium heads. So here it's a new power plant that we're building in Valais. So it's almost a 1 gigawatt power plant that we use between the two existing lakes. And it will be in operation, I think, next year or the year afterwards. As you see, these are big projects that are big investments. So luckily, I mean, Switzerland is in a economical condition that allows also to do this kind of big investments, looking, let's say, at the future. And so this will be a key technology, among others installations, in order to balance the supply and demand with more and more renewables in the Swiss energy strategy. The second technology that we see is so as I said, we can use the potential energy of storing water. We can also use the potential energy of storing air. So the principle again is pretty simple. What we can do is that we have excess electricity in the grid. We use this electricity to compress air. We store this compressed air in a cavern, let's say in a cave, where we can store high pressure fluid. And then we expand it in a turbine to produce back electricity to the grid, okay? So here it's pretty easy to do the math. Actually, here I'm considering what is the physics. The physics is from, let's say at least theoretically, is from the compression, isothermal compression of an ideal gas. So you can pretty easily derive the maximum, let's say, theoretical energy density that you will have if you compress air at the 200 bars. So you see that here we are talking about 410 kilojoule per kilogram. Just to give you an order of magnitude, this is more or less what you can store in a good in a lithium-ion battery. So I would say it's much higher than what you can store with hydro in terms of volume. It is in the order of magnitude of a battery. And you basically have three types of heat storage, compressed air storage. Let's say the most efficient one would be theoretical, would be the isothermal, in which you're able to compress and to turbine, to do all the process at constant temperature. But with real gases, in reality, temperature increase when you compress air. So you have two kinds of systems that exist. One would be the adiabatic, in which you're able to recover the heat from compression and use it back in expansion. One is the diabatic, which basically means that the heat generated is just removed from the system and lost, and the heat you need back, you need to provide it by the combustion of a bit of fossil fuels. And the only commercial existing system right now is the diabatic system. So if you look at existing power plants, so these are the real applications. So normally you don't get to 200 bars as in the calculation you saw before. Normally you get to 100 bars. The round trip efficiency, which means electricity back to electricity, can be estimated in the range of 50–60% normally. We'll see you can get theoretically higher, but that's the reality today. And you would use normally either depleted gas fields or even old tunnels and army bunkers, for example in Switzerland, in order to store electricity. As I said, the existing plants today are the diabatic plants, so the ones in which you need to burn fuels, and there's actually some pretty big one already existing since many years in Germany, for example. I show you a little example of a new technology that is being tested actually in Switzerland, in Ticino. So this is an adiabatic thermal energy storage that can reach efficiency of almost 72%, and it does this because it is able to recover the heat. So this is a very short video to demonstrate how this one works.
Basically, the system uses excess energy from the grid to pump pressurized air into a cavity within a mountain. The air is then cooled down using specialized technology called thermal energy storage, and then stored within the pressure cavity. When it's time to generate electricity, this air is then heated up again and pushed out to run a turbine that produces electricity. With this system, Alakai's claim over 72% round-trip efficiency.
So the idea here, the key advancement of this technology compared to another one is that you have, that doesn't work. Is that you have, you store the air already in the pressure chamber. And so you keep the air stored at high pressure. This allows you to recover the heat. So as we talked about pumped hydro and compressed air, two quite simple technologies, at least conceptually to understand, using the potential, using mechanical energy, let's say. There is a last technology that uses mechanical energy, and is the flywheel. So flywheel, again, is relatively simple to understand. Let's look quickly. This is the last video that I have to show you the working of some technologies.
Energy storage flywheels have very high performance and work with simple principles. To understand their operation, it is best to start with the electric motor generator. An electric motor and generator are really the same machine running in opposite directions. When you put electrical energy into a motor generator, it turns into mechanical energy on the spinning shaft. That's a motor. When you put mechanical energy into the motor generator by spinning the shaft, you can draw electrical energy back out. That's a generator. For an energy storage flywheel, we hook a motor generator up to a wheel. When we put electrical energy into the motor generator, it accelerates the wheel, storing that energy as momentum on the wheel. When we want our electricity back, we let the momentum of the spinning wheel drive the motor generator, regenerating our electricity and slowing the wheel.
Okay, so the idea there is pretty simple. You might have studied also, if you have a mechanical engineering background, flywheels in cars is a quite common technology. The idea is quite simple. So you store kinetic energy. So this is the formula. You remember kinetic energy is normally 1/2 times the mass times the speed squared. This is translational kinetic energy. rotational kinetic energy has the momentum of inertia instead of a mass, which depends on the size of the object, and the rotational speed instead of the translational speed. So again, the momentum of inertia depends on the shape of the object that you're using for storing the material. And in the case, normally what you have is an empty cylinder with a thin, what is called a thin rim, so a surface, which is the most efficient way to store normally energy in flywheels. And so the equation that you have is this one. So if you want an efficient flywheel to store a lot of energy, you have to increase the mass, you have to make it big, increase the radius, or increase the rotational speed. What are the limitations to this? Well, the limitations are normally materials. So we have the tensile stress of materials, the maximum that can be withstood by the material here, which is directly related to the maximum energy density that we can store in a flywheel. And so basically we have two types of flywheels again. One is the most standard ones, which is basically they are made of metal or steel and so on. So they have a high tensile stress, but they also have a high density. So they are a bit limited in terms of rotational speed and so on. Or you have new technologies, let's say advanced flywheels, which use polymers, reinforced polymer composites, which can couple a very high sigma in terms of tensile stress that they can stand to a low density, so they can achieve higher rotational speed. Flywheels, where do we use them? We normally use them, well, in cars and so on. We have them in various applications. In terms of the grid, so for balancing energy storage, they have a very fast response time, and also they are subject to relatively fast discharge. So normally we use them for short-term applications, for balancing the frequency of the grid, because we can change the speed very quickly, and we can put them connected to the grid, and we help balance. You know that the grid has to stay, depending on the country, at 50 or 60 hertz. It can vary really not much out of that, because that will cause like a blackout of the system. So these technologies allow for frequency stabilization and power regulation in the system. You would not store for very long time energy in a flywheel simply because friction will eventually stop it. Unfortunately, we cannot do perpetual motion, so we have to eventually. This kind of technologies is very efficient, but we use it for short-term storage. You see an example of a power plant that uses this. In the US, for example, this is a 20 megawatt power plant, so pretty big, with 200 flywheels. And what they do 5,000 cycles a year, so they tend to run pretty quickly and then stop. And the company here that implements this technology, they say to the TSO, so to the service operator, the service we provide you, you pay us, what we give you is we give you an additional tool to keep your frequency stable. Okay, so it's more grid regulation technology. So do you have questions up to now? Is it more or less clear? Okay, so let's, about the overview, we finish with, let's say, mechanical energy technologies. We have also the possibility of storing heat. So storing heat, basically, it's all it's all a series of technology that store thermal energy in order to reuse it later for heating or cooling purposes. So the first category of technology, they are divided normally into three categories. The first one is what we call sensible heat storage. So again, the equations, the physics is pretty simple. We store energy based on the mass times the Cp of a given fluid times the delta T. And the sensible heat storage means that we have only variation in temperature in our fluid, we don't have changes of phase and so on. If we want to do long-term storage with these kind of technologies, we can do what is called underground thermal energy storage. We can be underground or in big tanks. Normally, if it's underground, it uses aquifers or boreholes as a way of storing energy, which means we store heat in big underground lakes or in big reservoirs, and we can reuse it at a later stage. And this can have a fairly long storage time. We have either similar technologies, the pit storage, which is more at the level of smaller use, and it basically use shallow pits that are filled normally with water and gravel to store energy. We have the possibility of storing, if we have high temperature heat, so industrial heat, for example, as Sophia Hausner, Professor Hausner showed for concentrated solar power plants, we can store heat in molten salts, which work at fairly high temperature. And again, you use only the sensible heat in this case. You have solid media storage, which basically, since water in tanks can have the problem of corrosion, you can use concrete or other materials in order to store energy in solid media which don't have this problem. So in buildings, there are applications using, for example, concrete or bricks. And then you have the most classical probably technology, which is the hot and cold water tanks. So basically heating and cooling down a water tank. If we want to have a higher energy density, then we have to go to latent heat storage. So latent heat storage uses the changes of phase of material. You might remember from previous courses that the coefficient of heat that you have, of heat exchange that you have of a phase change in fluid is much higher than the coefficient you have of heat in the water. So when you boil the water, the heat transfer coefficient is much higher than when you heat it up, okay? So you can use this principle also for storing technology, and also you have the advantage that the temperature, of course, during change of phase of one fluid remains constant. In this case, one application is what is called the ice storage. Ice storage is normally used for air conditioning. It means you have excess electrical energy at some point, for example, during the night. You use it to create ice, so in a refrigerator cycle with a heat pump, and then when it's warmer during the day, you melt this ice in order to have the cold water that you can use for direct cooling, for example, in your building, or as a cold source of a heat pump. Or in general, let's say this goes under the category of phase change materials, which are generally material that you use because you want to store. During the heating process, they absorb some energy, and they have the change of phase in one direction. And then when you cool them down, they have the change of phase in the other direction, and then they release energy. And the third category, more at the research phase, is the thermochemical heat storage, which basically means you can have reactions, so chemical reactions that need heat or produce heat in order to happen. And in this case, if you have, for example, an exothermic reaction, you have heat available. If you have an endothermic, you need heat. And you can play with this, so reversible reactions, you can play back and forth in order to store thermal energy. Okay, so this is an overview of what you can do with thermal energy storage. Here is just, I let you in the slides this table in which I collected the key data about all these technologies. Of course, the goal is not that you remember that by heart, but that you remember more or less when you use one technology or the other. I show you an example also of this one. This is a district heating of Turin in Italy. Actually, it's a pretty big district heating. It's 500 kilometers and 2.4 terawatt hours a year. You can see here a big application of thermal storage capacity. You see that the system basically works out of only cogeneration, so cogeneration of heat and power using gas. And the storage component is quite big. You see that the charge and discharge of accumulators is a substantial amount of the heat. So you normally, when you want the cogeneration to run also in periods in which you don't need the heat, so you save this heat for later use, and then you reuse it when instead it is more convenient, it is less convenient to use the cogeneration unit. Okay? So just to show you that these things and these technologies can be used at relatively big, relatively large scale. And another thing which is interesting is how you can use thermal storage to smartly regulate the grid. So this is an example in France. In France, almost 1/3 of a house has electric heaters connected to the boiler, to a storage tank. These electric heaters can be controlled remotely by the grid operators. So what they do is basically they have excess electricity, they charge the storage tank of the houses, so they produce heat with electric heaters. And don't tell this to Francois because, of course, you learned that electric heaters are horrible under an energy efficiency point of view, right? But anyway, it is a way to use this excess electricity. So you produce heat, Joule effect, 100% efficient, which is why we shouldn't use first law efficiency. And you can use that to regulate, to use the excess heat, and to then use the heat when it's needed in the houses, okay? Francois would be happier with this kind of system. So if you give him a heat pump, what you could do is the same exact principle. You can store the heat, but of course you can store it by using a heat pump and then a reversible engine or an organic rankine cycle to recover the heat to give the electricity back. But this just to tell you that we don't have only to think of storing the kilowatt hour of electricity. We can be, and we will need to be smart in the future. So we need to think, okay, can't we convert this thing to heat or to ice? Or can't we charge an electric vehicle and use the electric vehicle as a storage technology that goes around and then connects back to the grid? So this is the kind of energy system we are going towards in the future. It's not anymore supply and demand. There will be probably storage technologies at different levels and with different technologies a bit everywhere to balance the grid at district scale and decentralized scale. Let's pass now to a quite well-known technology. So for who of you is Italian or at least is old enough, you might remember that in the 10,000 lira that we used to have before 2001, there was the picture of Alessandro Volta. So this is the introduction to the battery. The battery is basically, very synthetically, uses chemical reactions in order to store electricity. Well, either to only give electricity or to also be used in the double direction. The technology that, if we look at how it works, we basically have a redox reaction. It means that we have a battery is always made in the same way. We have two cells. One is the cathode, that is always the one that gains electrons, so the one that gets reduced. One is the anode. In this case, it's the negative side, which is the one that loses electrons, so it gets oxidized. And in the middle, between the cathode and the anode, we have a conductive electrolyte, which does not conduct the electrons. So we create an imbalance of charge, which, if we put a load on it, can can give electricity and provide needs, right? This is the technology, actually, how Volta first did it. Actually, it was made out of copper as cathode, as zinc as an anode, and the electrolyte was basically a solution with mostly water. Technologies of batteries haven't changed much since then. Actually, they have evolved a lot, but the principle remains the same. There has been more and more understanding. You'll see talks about new batteries every day. So there is a technology that is rapidly developing, that the concept remains always the same. And just to show you an example, for example, the lithium-ion battery, the one that you normally found in cell phones, for example, for portable application, and also normally in electric vehicles. So the principle is the same. Just to show you an example, here at the cathode you have lithium. At the anode, normally you have graphite, so carbon. And what you do is basically that the anode, as I say, loses electrons, the cathode gains them. This creates positive lithium ions that go in the other direction, and this generates a flow of current. And the key idea here is that this cycle is quite known, and of course we can use it by charging and discharging for storage applications, right? What kind of storage applications? Well, normally, if we look at the energy density, we see that it's a relatively low energy density, so it's higher compared to pumped hydro. It is on the same order of magnitude of, you remember before I showed you the theoretical energy density for compressed air energy storage was 400 roughly kilojoule per kilogram. Here we are around 500, for example, for a lithium-ion battery. So let's say average energy densities concerning the storage. It is a relatively efficient way of storing energy, but it is, due to the losses that you have inherently in the battery, it is a relatively short-term technology. Actually, it can be in the order of magnitude of some seconds to some hours. You won't use a battery in order to do seasonal storage, for example, of electricity due to the losses that you have. And just to show you here an example, so the key types of batteries have been almost always the same in the last years. I actually put a slide only on Moodle, not here, about some new developments, if they interest you. There are, for example, liquid metal batteries or vanadium flow batteries. So this is a bit where research is going today in order to increase energy density. I just wanted to show you that batteries can be used, and are already used today, for example, in wind farms, in order to balance the output of the wind farm. So we said wind is intermittent and so on, so power plants, wind farms can come already with fairly large battery, which are shown to be able to compensate quite a lot of the variation that wind farms have in order to send it to the grid. And you have applications of large size cores with normally lead acid battery, so again using lead as the main material for the electrodes. You have the same kind of application also with lithium ion batteries that are normally, though, right now used mostly in portable application and in electric vehicles. And you have other kind of battery, probably the most used one is the NAS battery. So this one is, for example, is sodium sulfur, and it is used for high temperature applications where you can, so applications in which you don't have constraints like in the houses or so on or in the cars to go very high in temperature, and you can increase the efficiency by working at higher temperature in this case. And looking at the last technology is probably the one that will play a major role in the energy transition. It is the idea of converting electricity to fuels, okay? So, why fuels? Well, because fuels have a very high energy density. We are talking about kilojoule per kilogram up to now for the other technologies. When we have fuels, you remember natural gas has around 45-50 megajoules per kilogram. Hydrogen is even higher, okay? So this storing electricity in fuels is one of the most efficient under the energy density way of using electricity. And we have technologies to do that. Actually, the technology is pretty simple. It's the same of a battery. So it's the electrolysis of water, in which we use, if we have a solution of water, with normally some salt in addition, and we have some metal electrode that can be composed of different materials, we can use the electricity in excess from the grid in order to separate in the same way we would do with a battery. So we have, in this case, the signs are inverted, so the minus is the one that gets reduced, the plus is the anode in this case, and you see that the reaction that, by the fact that you have a change in polarity between the two metals, you are able to attract hydrogen to the cathode and oxygen to the anode. So you're able to separate the two materials at an efficiency, the two elements, at an efficiency which is around 70 to 85%. So you can produce hydrogen with a relatively well-known and efficient technology. Power to gas concept can work in various different ways. For example, this is a concept that it's quite commonly envisioned for the energy transition. The idea here, for example, is to take the electricity, have electrolysis either in a normal electrolyzer or in a reverse fuel cell. You'll understand more about this technology in the next lecture. So you can see that, for example, you can store hydrogen. On the other side, you can take biomass, as you saw in the lecture with Professor Maréchal some time ago. You can do methanation, so you can extract the CO2. You can do methanation in order to transform, to add hydrogen to CO or CO2 in order to create CH4, so create methane. And at that point, the mixture of CH4 enriched by hydrogen is basically natural gas. So you can inject it directly in the gas grid, and then it's part of the grid. The other option can be, for example, using the CH4 in this case, or the hydrogen directly for mobility. So you see, again, an application of a sort of smart system that you will find more and more applications of this in the future. And the technology that you have implemented in your model, and we'll see it a bit better later, it's in the model that you have in the project, you have a power to gas to power concept. So what you have is that you're using a reversible fuel cell that in a fairly complicated system, but conceptually what it does is that it takes electricity, it converts it to natural gas, it liquefies the natural gas to store it in a liquefied natural gas tanks, and then when electricity is needed in the system, the natural gas is used in order to produce electricity back. Okay? So this is the system that you have currently implemented in the power to gas technology in the model that you're using. Yes?
Does this uses a lot of water in the process? Or?
Yes, you have quite a lot of water consumption in this process. Yeah. Yeah, I mean, let's say this is a fairly. We decided to implement this technology because it was it is let's say an advanced technology claiming up to 55–58%. So we wanted to show what is available for research. What you normally can do is directly converting, as I was showing before, electricity to hydrogen, mix it with CO2 in the methanation, and produce CH4 directly without all the conversion process that then needs it to store it to liquefy natural gas. So this is anyway the one you have implemented in the model at the current stage. Just to conclude about storage, so I will show you later how this is, for example, implemented in the model. I'll skip this part right now. I just wanted to show you that some statistics that, of course, with the penetration of renewables, it is forecasted that we have more and more storage in the future. Also, you see that in many reports, you find the indication that electric vehicles will be a sort of competitor storage technology. So the fact of having electric vehicle could balance out the needs of electricity in the grid by, let's say, smart charging and so on. And you can see also that most technologies are expecting to have a very strong reduction, especially when it is related to batteries. Most technologies are really diminishing in cost very, very quickly. Okay? So I will, I have added some slides that I'll just go through quickly here. It's just to, we will see them later in the second hour. It's just to show you that how storage is implemented in the model, what technology we have added in the energy scope model. So if you're interested in checking the equations, I put them in the slides, but you're not requested, of course, to know these things. It's mostly for your personal knowledge. What I would like you to recall from this lecture is the key difference between the storage technologies that you have available. So long-term storage, for example, with pumped hydro and compressed air storage, batteries acting more at transmission and distribution level, and others more technologies, for example, heat storage and so on, that are mostly on the demand level. And for each of them, what you should recall is mostly what are the main principles that they have, and what are the key efficiencies and energy densities. Okay? So I propose you to start again at 12, so in 12 minutes. Let's say so Luis will give you a general feedback about the milestone, and then we will discuss a bit more, and if you have questions about the project and the model and so on, this will be the right time to ask them in the second hour.